So what we are doing today is that we are starting the discussion about point defects. So we will actually talk about defects in materials in general. And the point defects are the simplest form of these defects. So we will see that many of the properties of the materials are governed by the presence of the defects. And we will see that, for example, one amazing thing that we will learn today is that the point defects are actually thermodynamically stable. What that means is that if someone tells you that they were able to design a completely perfect crystal at room temperature, you know that they are telling you something that is completely incorrect. What that means is that we will learn that at a given temperature that is not 0 Kelvin, you are expected from the thermodynamics principles to see vacancies and other types of point defects. So this is one major theme that we will cover today. So, but before we do start, I would just like to remind you that what we did last time, and let me just see how I move this. Let me just try to move it here, perhaps. So what we talked about in this semester is we talked about amorphous materials, but then we covered the topic of the crystalline materials, and specifically in the last two lectures, we talked about liquid crystalline materials. So as I mentioned, we will talk about microstructural imperfections for the rest of the semester. But before we do, I just wanted to give you an example of a very exciting thing that happened that I actually read yesterday. So there was a paper that was published in Science where they used, you're probably familiar with the journal Science, right? So it's one of the most famous journals in science in general. But what they did is they used liquid crystalline materials to direct bacteria. So that happened yesterday. I read this yesterday, and I was really excited about this. So apparently, there are some self-propelling bacteria. So these are the bacteria that have anisotropic shape like liquid crystals. And in general, at room temperature, for example, they will move in Brownian motion. So in principle, you cannot direct their motion unless you have a physical way to confine them. So this particular paper described a way, so when they put these bacteria into a liquid crystalline material, they can actually direct the bacteria. So what you see here are the lines in this image are the bacteria, and this is the corresponding liquid crystalline structure, and you can see that they follow. So you know, on the problem set 5, you have one question about the applications of the liquid crystalline materials. So one of them can be direction of the self-propelling bacteria. Okay. So again, what we are talking about for the rest of the lecture today is we are starting that discussion about equilibrium defects or point defects in materials. So the reason why we are talking about these types of things is that we learned about, for example, crystalline materials and symmetry. And we talked about the Newman's principle and the fact that you can predict whether the material will be isotropic or anisotropic, right? And if you, for example, know what is the electronic structure of the atoms that constitute that material, you can say, well, in principle, we can calculate the bonding type, we can calculate the strength of the bonds. And from that, for example, we can calculate the mechanical properties or even electrical properties of that material. And when I talk about this, calculate, I mean the magnitude of the property, right? So when we talked about the structure, we talked about whether that particular property is isotropic, anisotropic, etc. But we didn't necessarily talk about the magnitude of that property. So you might be tempted to say, well, if you know details about the atomic structure of the material, you should be able to calculate those things. And in principle, yes, you can calculate them. But when you, for example, experimentally measure plastic deformation of the materials, etc., you learn that these experimentally measured properties are dramatically different from what you would predict, right? And the reason for that is that if you're assuming a perfect crystal, it is very, very different from the actual materials that we observe in everyday life. And in fact, defects, point defects, dislocations, etc., actually govern most of the properties that we know about in materials. And again, I'm here talking about the magnitude of these properties. So some of the examples of these properties would be, for example, conductivity in semiconductors. So for example, if you have a semiconducting material, silicon, germanium, gallium arsenide, etc., the way how you control the electrical properties or the conductivity is by the level of the dopant atoms, which are actually point defects in these materials. Another example, do you know any type of property? Can you give me an example of a property that is governed by defects? not necessarily point defects, any defects. Yes?
Work hardening in metals?
Work hardening, yes. So this is related to mechanical properties or plastic deformation materials, right? So you will see that, for example, the way and the magnitude of the stress that you have to apply on a material to deform it plastically depends on the density of the dislocations in that material. Okay, so for example, plasticity. Any other example? Yes? Excuse me? Color. Can you tell me? Yeah, excellent. What do you mean by color?
If you add defects to glass, you can change the color of much different. Like rubies are.
Yes. So, for example, there are different classes of materials when you introduce impurities or point defects. You will change the color of that material. One example would be diamond. So, for example, if you introduce nitrogen types of defects, they will completely change the electronic and the optical properties of that material. Color is an excellent example. Okay. So, any other examples? For example, diffusivity. If you have two materials and the diffusivity in these materials will also, we will see, depend on the concentrations of vacancies. And there are many other examples, and these are just some of them. Okay, so when we talk about defects in general, we will talk about their dimensionality. What that means is that depending on the scale and the dimensionality, we will talk about point defects, which will be zero-dimensional. We will call them zero-dimensional defects or point defects. And these can be either vacancies. What that means is that if you have a crystalline material, like this one shown in blue, if you simply take an atom outside of that material, this would be considered a vacancy. So most of today's discussion will be actually on vacancies. So they can also be interstitial atoms. So what that means, again, if you have a crystalline structure, if you take a foreign atom and you introduce this into the crystalline structure, example would be a small atom, for example, carbon in an iron matrix. So this would be called an interstitial impurity atom. Or, for example, the next type of point defects would be substitutional atoms. What that means is that if you have a matrix, let's again iron, and if you replace one of these atoms in the crystalline structure with another type of an atom, this would be called a substitutional atom. They are all considered to be point defects because we are talking about individual atoms that we are either removing or replacing or introducing into the existing matrix. So then the line defects or one-dimensional defects will be called dislocations. And an example of dislocations would be this image here. So this is a transmission electron microscopy image. And the lines that you see here are the dislocation lines that propagate through this material. And the reason why they are called one-dimensional is because there is a collective behavior of atoms in one dimension that contributes to the presence of these defects. And we will talk extensively about dislocations in metals and other materials in more details. Then the two-dimensional defects will be, for example, grain boundaries, phase boundaries, stacking faults, etc. And again, an example of two-dimensional defects is in the third image here. And again, they're called two-dimensional because, again, we do not necessarily depend on individual atoms, but on their collective behavior in one particular plane of a crystal. So if you, for example, have two phases in a material, then the interface between them would be called a phase boundary. If you have the same material with different orientations of the grains, that would be called a grain boundary. So the colors here in this particular image and the lines between them correspond to either grain boundaries or within an individual grain. For example, in this particular image, this would be a so-called a twin boundary. And finally, three-dimensional defects very often are not considered to be defects, but part of the microstructure of the material. And so these are precipitates, voids, etc. So for example, precipitates would be an existence of a particular material in a matrix of a different material. Okay?